Hi, and welcome to our Types of Chemical Reactions podcast. So in this podcast, we're going to go through the 5 basic types of chemical reactions, and we're going to talk about how to approach a word problem that doesn't tell us what products are produced. So our first type of reaction is a combination reaction. These are also referred to sometimes as synthesis reactions, so you may see it both ways. Either one would be fine for us in class. You can call it by either. And this is where you have 2 or more elements or simple compounds combining, and the kicker is they are going to form one product. That is what we're going to use to classify this. So as we go through each of our reactions, I'm going to show you a generic reaction using letters A, B, C, and D to try to emphasize what you're looking for. So in a combination, single element plus single element forms a single compound or a single product. And we see this in our visual. We have element A plus element B forms the compound AB. An example of this in real life would be when we take magnesium and we stick it in a Bunsen burner flame in the presence of oxygen, and it forms this whitish powder, this kind of ash that's called magnesium oxide. Again, magnesium is your element A, oxygen is your element B, and we form one single product, one compound, AB. All right, so as we go through these, I'm going to start us a little cheat sheet, and we're going to see this in the bottom corner of your screen. This cheat sheet would be a really good thing to have as you're working practice problems until you start to memorize this. So I know combinations are always going to be A plus B forms a single compound AB. Our next type of reaction is called a decomposition reaction, and this is where you start with a single compound and it splits into 2 or more simple elements. So using that generic equation, we start with a single reactant. This is how we can find decompositions. They only have a single reactant, and those reactants are going to split apart or decompose into 2 smaller or more simple elements. So here we have compound AB splitting into element A and element B. And in our visual, we see exactly that. Your compound becomes 2 products. So a single compound forms 2 products. In an actual example, we can talk about mercury 2 oxide splitting or decomposing into mercury and oxygen gas. Again, let's go ahead and update that cheat sheet so that you have a nice little reference card that you can use in order to solve problems. So again, we're going to add decomposition to the list. Now notice the differences we see between these. They're almost like opposite reactions. In a combination, A and B are coming together to form a single product. In decomposition, a single reactant is splitting apart to form 2 or more products. Our next type of reaction is a single replacement reaction, and this is where you have one element replacing another element in a compound. So this gets a little bit trickier. So we're going to have a single element all by itself, and the way I remember this guy is there's this loner element, a singleton, a single guy, sitting all by himself, and then there's this compound, and I don't know why I like to think of them as couples. I really don't. Anyway, we have a compound and we have an element. And what happens in this is your cations or your metals are going to swap places. So B was part of a compound, and now B is all by himself. He has been replaced by A. A was single, and A has now combined with C to form a compound. Looking at our image, we see the same thing. Single element A plus the compound BC. We see that A and B have swapped places. B is now all by itself, and A has replaced B in the compound AC. An example of this would be zinc and hydrochloric acid. Now, remember that I said to make this easier, you're going to swap your cations. So metals are cations, and this is also going to include the non-metal hydrogen. So zinc and hydrogen are going to swap places. So zinc is now in a compound with chloride, and I'm going to have to double check my charges and drop and swap when I'm doing this on my own. And hydrogen is now all by himself, but remember that hydrogen's diatomic, which means anytime he's by himself and not bound with another element, we have to put a 2 in the subscript. Let's update our cheat sheet. Okay, notice here we have, for the first time, an element and a compound in our reactants, and we have an element and a compound in our products. Our next type of reaction is a double replacement. So in this situation, we have two compounds that are going to react with each other, and your positive and negative ions are going to switch places with each other. So let's look at our generic equations. We have compound AB and we have compound CD. To keep things straight, I like to switch the cations, or the positively charged elements. Those are your metals. Those are the ones that come first in your formula. So A was partnered with B, but when we swap places, A is now with D. C was your metal that was with D, and now C is with element B. So we have two cations swapping place, or we have a double replacement. Nobody is single and off by himself. And looking at our visual aid over here, we have AB and CD, and all we see is that A and C swap places, forming new compounds, AD and CB. If we were to look at this in an actual example, we can talk about the compound barium chloride and sodium sulfate. Now in this, again, just to keep us straight, because you're not always going to be given the products. Sometimes you have to predict the products based on what type of reaction you're looking at. Here we have our cations, barium and sodium. Again, looking at those metals, we know that they're going to swap places. So barium is now going to be with sulfate. I got to check my charges and determine my new subscript. And sodium, instead of being with sulfate, is now with chlorine. So our new compounds have formed as a result of the swap of those cations. Again, updating our cheat sheet, I want you to take a look at the differences between single and double replacements. In a single replacement, you have a single element in the reactants, and you're going to wind up with a different single element in the products. Whereas in a double replacement, you're going to have two compounds in your reactants and two compounds in your products. Our last type of reaction is not covered in your book, and it is by far my favorite reaction, and that's the combustion reaction. This is where you have carbon and hydrogen are going to react in the presence of oxygen, or they're going to burn in the presence of oxygen, and you guys are going to get to do this in lab. And the products of this reaction are always the same. They're always going to be carbon dioxide, water, and energy. So looking at our generic equation, I put X's in here. You always start with carbons and hydrogens. I don't know how many. That's what the number X represents. They're always going to burn in the presence of oxygen, which is diatomic, so we always say O2. And they're always going to form carbon dioxide and water. What they're going to do as well is they're going to give off a great deal of heat, or excuse me, a great deal of energy in the form of heat and light. So here's an example of CH4. I have one hydrogen and four, I have one carbon and four hydrogens. This is methane. And it is burning in the presence of oxygen, and it's going to produce carbon dioxide and water. Notice that we had to balance this equation. It's also producing a good deal of heat. So this one's probably the trickiest one for students to identify, simply because we're like, oh, it kind of looks like a single replacement. We have a compound and a single element, and so they want to switch those. So be very, very careful that anytime you see carbons and hydrogens and oxygens only, it's combustion, and your products are CO2 and H2O no matter what. This is one of my favorite examples of these reactions actually happening, and that is that reaction that causes your airbag to inflate should you be so unfortunate to get into a car accident. So if you have a crash, it's going to trigger sodium azide, which we don't really deal with, so I'm just going to write that out for you. Sodium azide. It's going to ignite, and it's going to form solid sodium and nitrogen gas. Okay, so when this ignites, it causes this reaction. This nitrogen gas is what actually causes your airbag to inflate. So that's the gas that fills the airbag. Unfortunately, sodium is very reactive, especially around water. We don't want that as a side product, so there will be a further reaction with that to form a harmless salt as a result. But what's really amazing about this is the time it takes for this sensor to identify that you've been in a crash, and for this reaction to happen and to fill the bag with nitrogen gas happens in 40 milliseconds. So it happens so quickly and almost immediately. And so this is a very neat example of a type of reaction. So notice that I have a single compound, and I'm using my generic terms because that helps me to identify what I get. And I wind up with a simple compound breaking down or decomposing into two individual elements. So I could classify this reaction as being a decomposition reaction. All right, so how can we put this to use? We can use our types of reactions to figure out what it is we're combining as our reactants to predict the types of products that we're going to get. And in order to predict the products that you get from a certain reaction, you're going to have to be able to classify that reaction. So we start by writing out neutral formulas for the reactants. Remember, if this is an ionic compound, you need to check the charges and drop and swap them so that you are forming neutral compounds. Once you have those reactants written, you'll be able to identify the type of the reaction. So I've got our cheat sheet here again, and I'll be able to look and see, do I have a single element plus a single element forming a single product? Okay, that's a combination reaction. I know those are going to come together. Do I have two compounds that are in my reactants? Because I know the cations are going to swap places, and we have a double replacement reaction. So this is going to take a lot of practice before it becomes more streamlined. You will predict products based off of your rules. You're going to write neutral compounds, and your last step is always going to be to balance the equation. So this is a little overwhelming in words, but don't worry, we're going to put this into practice on the next slide. All right, so let's go ahead and practice balancing some of these equations, predicting products, writing equations, not in that order. Okay, so we were told that ethyl alcohol burns in air, and they gave us the chemical formula for ethyl alcohol as being CH3CH, that's a terrible H, 2OH, and when we say burn in air, that's always O2 because it's a diatomic element. So now this is probably the most difficult task that I have, and I'm going to have to figure out what type of reaction this is. So I'm going to go through my list, my cheat sheet. It is not a single element plus a single element. So it's not going to be a combination. It is not a single compound to start with, so it's not a decomposition. Now here's the tricky one. Single replacement kind of looks right, but I'm going to go through my entire list just to be sure. I have a single element, which is oxygen, plus a compound, which is represented by Bc. I know it's not a double replacement because we don't have two compounds. We also don't have any metals or any cations that we could switch. These are all non-metals, so that should be a red flag to me. So I know it's not a double replacement. The other option is that it's a combustion. And so in a combustion, we have a certain number of carbons and hydrogens and oxygen. Well, that's exactly what we have here, is we have carbons. Now, they don't look exactly like the formula, but we have carbons, hydrogens, and oxygens only. If it were a single replacement, we would have a couple of metals, and those cations would swap places, and we just don't have any cations in this. So I'm going to go with a combustion reaction for this. I have to actually spell it out because comb could be combination as well. It's a combustion. And as we talked about earlier, combustion reactions always have the same two products, CO2 and H2O. So there's no swapping around, there's no thinking about it, it's just always those two products. So now my task is to balance this, and this is a beast to balance. All right, so let's start with our carbons. On my reactant side, I'm drawing my line in the sand, I have 2 carbons on this side, and I have 1 carbon on the other side. So I'm going to go ahead and put a 2 in the coefficient because 2 times the subscript 1 is 2. And now we have 2 carbons. This will be challenging because if I have to change my coefficients, I can't erase them or you're never going to see what I'm writing. So I will cross them out and put the final answer in a different color. All right, now let's move on to hydrogens. Here I have 3 hydrogens plus 2 hydrogens plus 1 hydrogen gives me a total of 6 hydrogens. Looking on the other side, I only have 2 hydrogens. So since this is my smaller side, I'm going to think what times 2 would give me 6, which is 3, and I'm going to put a 3 in the coefficient spot. So now I have 6 hydrogens on each side. My hydrogens, my carbons are balanced. Now for the oxygen, we're going to work it backwards. We're going to start on the product side and then go back and look at the reactants. So I have oxygen in 2 different places. All this means is I'm going to tally up each compound and I'm going to add them together. So here I have 2 times 2 is 4 oxygens, plus 3 times 1 is 1. I'm sorry, it's not 1. That's embarrassing. It's 3 oxygens, so I have a total of 7 oxygens. Odd numbers are not good. If I look back at the other side, don't let this guy sneak by you. I messed this up once and I totally didn't see him there, but I have 1 oxygen here, and then I have 2 oxygens over here. So because we have an odd number, we have a little bit of flexibility here. If I can, I do not want to change the coefficient in front of my ethyl alcohol, because then I have to go back, I have to change all my carbons and all my hydrogens, and it's a big fat mess. So I know I'm trying to get up to that magic number of 7. If I subtract this 1 oxygen right here, I know I have 6 left to account for. So omitting this oxygen, so I've already accounted for him. I don't have to multiply his subscript. I know I have to come up with 6. Well, if I multiply this O2 by 3, I will have 6 oxygens here plus 1 oxygen in ethyl alcohol for a total of 7. All right, that was a tricky one. I'm glad we got that out of the way. Let's look at the next problem. All right, so now we have sodium reacting with aluminum carbonate. So I'm going to start by writing out the word problem so that I can identify what type of reaction we have. So here we have sodium. It is a metal by itself. It's not diatomic. I don't have to put any subscript. Reacts with is a fancy way to say plus. And I have the compound aluminum carbonate. So right up here, just kind of out of the way, I'm going to write my charges because I can't erase this for you, and I can't have any charges in my final answer. So I know aluminum has a +3 charge and carbonate has a 2- charge. So I'm going to drop and swap these guys. So my neutral compound should be Al2, and then I have to use parentheses because I need 3 of those carbonates to balance out my 2 aluminums. All right, that's all they gave us. So now we have to determine what type of reaction this is. Well, it's not a single element plus a single element, so it's not a combination. I don't have a single compound to start with. It's not going to be a decomposition. What about this one? I have a single element, sodium, plus a compound, aluminum carbonate. In this situation, I do have 2 metals or 2 cations that can swap places. I'm pretty confident that this is a single replacement. So I'm going to proceed. I know that my cations switch places, so now aluminum is going to be all by his lonesome, and sodium is going to be now with carbonate. So I'm going to just double check off to the side what my charges are. Sodium is +1, carbonate is a 2-. That means that I'm going to need 2 sodiums for every single carbonate in order to have a neutral compound. All right, so let's balance. Drawing my line in the sand. Ooh. I know I have 1 sodium on this side and 2 on this side, so I'm going to put a 2 in the coefficient spot. I have 2 aluminums here and only 1 here, so I'm going to put a 2 on the lower side. 2 times 1 gives me 2. Now I have a decision to make. If carbonate is intact as a carbonate on the other side, and it is, I can count this as a single unit, which would be a lot faster. So here I'm told I have 3 carbonates. And on this side, I have no parentheses or subscript, and I also have no coefficients. So I only have 1 carbonate on this side. So I'm going to go to this side that's smaller, and I'm going to say 3 times 1 will give me 3 carbonates, but it changes my number of sodium. So now I have to go back. I now have 6 sodiums. So I have to go back and change this number. You can please erase this on your paper. I'm going to change this number to 6 because 6 times 1 gives me 6 sodiums on each side. And we are finally balanced. And oh my God, that was almost a 20-minute podcast. I am so sorry. We're done.